Students, in this lecture, we'll discuss about Nyquist plot analysis. So, whatever is a concept of Nyquist plot, it is based on the polar plot which can be conveniently applied to the stability analysis of any kind of system. So, whatever is this concept, it is somewhat different from that to understand, and because whatever is a procedure that has to be followed, it has to be carried step by step in Nyquist plot. The first one is step is pole zero configuration from Nyquist plot point of view. Second, concept of encirclement and number of encirclements. Third, analytic function and its singularities. Fourth, mapping theorem or principle of argument. Fifth one is Nyquist stability criteria. So this will be based on this step by step the discussion. So next we'll see about pole zero configuration. Pole zero configuration. Okay, pole zero configuration. So it is said that any function which can be expressed as a ratio of two polynomials has its own poles and zeros. So we'll consider a function g of s, h of s called open loop transfer function of a system. Then the poles of g of s, h of s are called open loop poles, and zeros of g of s, h of s are called open loop zeros. So we'll consider closed loop transfer function c of s by r of s. So how we can write c of s by r of s, which we have already seen in the basics, as we can write c of s by r of s as g of s divided by 1 plus g of s into h of s. This has already been discussed. Then whatever are the poles of this particular transfer function, they are the roots of the characteristic equation. So what is the characteristic equation? 1 plus g of s, h of s is equal to 0, and they are called as closed loop poles of the system. Closed loop poles of the system. Okay. Now we'll take an example. G of s, h of s is equal to 10 divided by s into bracket s plus 2. Then open loop poles are, so it is given g of s, h of s. So open loop poles are s is equal to 0, s is equal to minus 2. So s is equal to 0, s is equal to minus 2. These are the two open loop poles. There are no zeros, as there is in the numerator nothing associated with s. Due to that, open loop zeros are absent. Now we'll take the characteristic equation. 1 plus g of s, h of s is equal to 0 is, so we'll write 1 plus g of s, h of s, which is 1 plus 10 divided by s into bracket s plus 2 is equal to 0. So we'll expand that. S square plus 2s plus 10 is equal to 0. S square plus 2s plus 10 is equal to 0. Now we have to find out the closed loop poles. Okay, closed loop poles. Now we have to find the closed loop poles. So the closed loop poles are the roots of s square plus 2s plus 10. So whatever is that characteristic equation, which we have got it as s square plus 2s plus 10 equal to 0. The closed loop poles are the roots of those characteristic equation s square plus 2s plus 10 equal to 0. Now we'll consider the mathematical function f of s is equal to 1 plus g of s, h of s. So we'll consider the mathematical function f of s is equal to 1 plus g of s, h of s. So we are now considering the function and not the equation. So we are considering the function and not the equation. So 1 plus g of s h of s is equal to 0. Okay, considering the function and not the equation. Okay, then whatever is this function, it can be expressed as a ratio of two separate polynomials in S as on its own. Okay, as f of s is equal to 1 plus g of s h of s is equal to p of s by q of s, p of s by q of s. Okay, then roots of p of s equal to 0, roots of p of s equal to 0 are the zeros of 1 plus g of s hs, whereas the roots of q of s is equal to 0 are the poles of 1 plus g of s h of s. Okay, g of s h of. Then whatever is, we have 1 plus g of s h of s, the LCM of 1 plus g of s h of s is always the denominator of g of s h of s. Then q of s polynomial is always the denominator of the function g of s h of s. Okay, so when we have q of s equal to 0, it gives the roots which we have called it as open loop poles of a system. So having the conclusion for this, poles of 1 plus g of s h of s is equal to open loop poles of the system. Okay, open loop poles of the system. Open loop poles. We'll consider ps is equal to 0, giving the zeros of 1 plus g of s h of s. But p of s equal to 0 gives an equation which is nothing but the characteristic equation of the system. So p of s equal to 0 gives us an equation which is nothing but the characteristic equation of the system, which gives closed loop poles of the system. So putting it in the conclusion form, zeros of 1 plus g of s h of s is nothing but closed loop poles of the system. Okay, closed loop poles of the system. So next we'll take a example. The example is, we'll consider a system which we already seen just now, with g of s h of s is equal to 10 divided by s into bracket s plus 2. Now we'll write f of s. So how we can write f of s? 1 plus g of s h of s. It is, we are considering the function but not the equation. 1 plus g of s h of s. So 1 plus g of s h of s will take the function. So we'll substitute 1 plus g of s h of s, which is given 10 divided by s into bracket s plus 2. So expand it, you will get s square plus 2s plus 10 divided by s into bracket s. This can be written as p of s by q of s. So q of s is equal to 0. So this denominator q of s equal to 0 gives poles of 1 plus g of s h of s. That is, s is equal to, will get 0 and minus 2. S is 0, s is minus 2. Will give the poles of 1 plus g of s h, which are called as open loop poles. While p of s is equal to 0 gives zeros of 1 plus g of s, that is roots of the numerator we are talking, s square plus 2s plus 10, p of s. Okay, s square plus 2s plus 10, which are the closed loop poles. Which are the closed loop poles. Okay, then so when we take the Nyquist plot point of view, the system is absolutely stable if all the zeros of 1 plus g of s h of s, that is closed loop poles of the system, are located in the left half of s plane. The closed loop poles of the system, which are nothing but the zeros of 1 plus g of s h of s, are located in left half plane of s, left half of s plane, then system is absolutely stable. Okay, so whatever is a stability criterion, what we have discussed, it remains the same but how it is, the way that is used to express, it is changed by analyzing the function 1 plus g of s h of s for its open loop poles and zeros. So this is what is called Nyquist criterion. Next we'll see about encirclements. Okay, so it is applicable for the paths which are open and not closed like polar plots. But for a closed path, there is a need to understand the concept of an encirclement. We'll consider a closed path tau of S in S plane as shown. Okay, we'll take this. Okay, as shown. As shown. Okay, a point is said to be encircled by a closed path if it is found to lie inside that closed path. So a point is said to be encircled by a closed path if it is found to lie inside that closed path. So it has to be lie inside the closed path. Okay, so when we see this figure, the points O, this is a point O, this is a point A. So the points O and A and all which are inside this path, this is a path tau of S. So you can see it has been repeated, tau of S is a path. So the points O, A and all which are inside the path are encircled by this path. Okay, so this concept is quite simple, but in some complicated closed paths it is possible that point lies inside the path, but actually not encircled by the path. So it is always better to count the number of encirclements of a point. So counting, now we'll discuss about counting number of encirclements. So whatever in this figure is above, this figure particularly, it can be easily concluded that number of encirclements of point A and O is 1. So how many encirclements are there for this O? Only 1. How many are this point A? Only 1. And you can say this is O point, this is point, but how is this like this? Here it is like this. So it is 1 in anti-clockwise direction. So if it is a complicated case, then it is not possible to judge number of encirclements by just inspection. Then there is one simple method for obtaining the number of encirclements. So what are the steps involved in finding the number of encirclements? We'll see. First, what we have to do to find how many number of encirclements, draw a vector from a point whose encirclements are to be determined in such a way to join any point outside that closed path in any direction. Avoid confusing directions. Second, so what we have to do, you have to draw a vector from a point whose encirclements are to be determined in such a way to join any point outside that closed path in any direction. Then avoid confusing direction. Second, identify the number of intersections of this vector with a closed path. 3. Mark these intersections with small arrow on the same vector indicating direction of closed path at the time of intersection. Fourth, cancel the oppositely directed encirclements. The remaining arrows gives us the number of encirclements of that point. Okay, so anti-clockwise encirclements are treated as positive, clockwise encirclements are treated as negative. Okay,